So let's do another example of centripetal motion. Let's consider a car driving around a curve. Okay, so we have a car driving around a curve, and let's say that this portion of the curve is actually like a fraction of a circle, has a radius of curvature of 29.2 meters. Okay, and the car, now what makes the car go around? Because the car wants to go straight. Newton's first law says unless there's a force acting on it, it's going to move straight in a straight line at constant speed. So there has to be a force acting this way. Well, if you think about it, think about the car on the road surface. So we have the car here, okay, and so there has to be a force. Well, the only place where there's contact between the car and anything else are the tires. So that means there has to be a force on the tires. Well, that's going to be static friction. So when you turn the steering wheel, then the tires, the front tires rotate, and so they're rolling, trying to roll in a different direction. The car is moving, and so that means there's static friction. That static friction is pushing to laterally. And so we're interested in the coefficient of static friction, and that's going to be 0.684. I saw a fantastic example of this that happened a number of years ago. There was someone driving along the road, and it was raining, and they were driving a little faster than they should have. They came up behind another car more than they should have. They hit the brakes. The car did not have anti-lock brakes, and so the wheels locked up. We already talked about how that means you went from static friction to kinetic friction. All of a sudden, the coefficient was much less, and so this car stopped slowing down. It was obvious they were about to hit, so the driver turned the wheel of the car. And so when she turned the wheel of the car, then nothing happened because we were no longer in static friction. It was a kinetic friction, and everything was sliding, so it did not matter what direction the tires were pointing. And so she just continued sliding in a straight line into the back of the car that was in front of her. And yeah, saw the whole thing. So I stopped and gave a statement to the police as to what happened, and resisted explaining to her the physics as to what happened. But at any rate, that's why, professional drivers, if they get into a skid, like race car drivers, what they do is they get off of the brake, they turn the wheels in the direction the car is skidding in order to get the wheels rotating, and then they have control, which means then they can try to take evasive action. So anyway, so we're into static friction right here. And so we say, okay, so we have static friction. Well, we look at it, and that static friction is what's providing the centripetal force. So we would say, therefore, that the centripetal force is going to be equal to the static friction. Okay, so centripetal force equals the static friction. So centripetal force is mv squared over r. Static friction is going to be mu sub s times the normal. Well, with the car sitting right here, on the road, we have mg down, normal, and so the normal force here would appear to be just equal to mg. So mv squared over r equals mu sub s mg. Well, it turns out that the m's cancel, so v squared equals mu sub s rg. So v equals square root of mu sub s rg. So that means we can find now the fastest the car can go around the curve, because we know all those factors right there. So v equals square root mu sub s rg, and that turns out to be equal to 14.0 meters per second. So that's the fastest the car can go around that curve. If it tries to go faster than that, then the car will break loose. And so if you try to go faster than that, then what happens is the car will just slide in a straight direction at that point. Race cars have this issue. As they're going around, if the front of the car starts to lose friction, the front swings out, okay, and they call that pushing. On the other hand, if they're going around and the back of the car starts to lose friction, then the back of the car starts to swing out, and they call that loose. Well, for race drivers, you want to go around a curve as quickly as possible. So we've got this curve here, and you want to go around as quickly as possible. So how do you do that? Well, we have several options. One option is you can change the coefficient of friction. The bigger the coefficient of friction, the bigger the speed. And so that means that you can go around the curve a whole lot faster. So racing tires have exceedingly high coefficient of friction. In fact, many racing tire compounds have a coefficient of friction that's greater than 1. Now, what does greater than 1 mean? It means the tires are so sticky that it's easier to pick them up and carry them than it is to drag them on the ground. And so now you don't get something for nothing. A coefficient of friction that heavy also means the tires get torn up rather quickly. So one set of tires is unlikely to last an entire race. Okay. The other thing you can change is R. So instead of following with the track, what you can do is follow a curve like this. So you dive in close to the inside here to go out to the outside on the outside. What that does is that makes a much larger radius of curvature, which means you can go faster around the curve by taking a different track around the curve. Now we're assuming flat curves. So we're not talking about banked curves. If you have a banked curve, then the racetrack itself actually gives you a normal force that's partially in the direction you're trying to go. And so that also helps you go around the curve even faster. Now, for a flat racetrack, you can change mu, you can change R. It'd be nice if you could change G. Okay. So unfortunately, it doesn't work that way. Now, if you were to go, for example, to Jupiter and race, then you would have a bigger G. You could probably go around the curves faster. Oh, but wait a minute. Where did the G come from? The G came from the normal force. We had mg pulling down, so the normal. So if I increased a downward force, that would increase the normal force. Instead of being mg, it'd be mg plus something. So that means that if I put aerodynamic surfaces on the race car that push downwards, a down force, that would increase the effective G, and that would make the G term bigger, which again would mean you would go faster. Okay, so that's some of the physics behind racing. It's very simplistic physics behind racing right there. It really gets way more complicated than that, but just just to get an idea as to some of what goes on. Now, let's remember, we're going around this curve at 14 meters per second. So we're just following like a regular streetcar out here in one lane of traffic. Now, assume it's a streetcar, a regular street legal car. You got the mirror, and let's say you got something hanging from the mirror, some fuzzy dice or something. And as you go around the curve, they hang at an angle. I want to know what's that angle. Okay. So you look at it and say free body diagram. We have mg pulling down. We have tension pulling at an angle like that. Okay, so if I look at components here, this is my angle theta, then obviously tension cosine theta has to balance mg. What's T sine theta doing? Well, you think about it, T sine theta, the horizontal component up here, that is actually what's pushing, because you have to go, the fuzzy dice or whatever that's hanging from the mirror have to go with the car around the curve, and so that means there has to be a force on them that way. So there has to be a centripetal force. So T sine theta is the centripetal force. Centripetal force is mv squared over r. So what I'm going to do is I'm going to take my equation here, take the first equation and divide by the second equation. So T sine theta divided by T cosine theta equals mv squared over r divided by mg. So the t's cancel, the m's cancel. Sine divided by cosine is tangent. So tangent theta is going to be v squared over rg. Okay. Well, that means theta is the inverse tangent of v squared over rg. Well, we know that v is 14 meters per second. We know that r is going to be 29.2 meters. We know g is 9.81 meter per second squared. So theta, the angle, turns out to be 34.4 degrees. Okay, so that's the angle that the object hanging from the mirror is going to make.